que comúnmente asisten a este seminario, pero también a los invitados. El día de hoy tenemos como invitado al doctor Shi-Hai. Una breve reseña de él. Es todo esto, pero voy a leer solo la mitad. El doctor Shi-Hai nació en 1969, es una historia muy joven, en Dalian, China. Recibió su doctorado en el Instituto de Física de Altas Energías de la Academia China de Ciencias en 1999. Después el doctor Dong se unió a el Laboratorio de Física Química Teórica de la Universidad de Oxford como profesor visitante. 2. A la Universidad Estatal de Kansas como investigador postdoctoral. 3. A la Universidad Nacional Autónoma de México como profesor visitante. 4. Al Instituto Mexicano de Petróleo como investigador postdoctoral y profesor visitante distinguido. 5. A la Escuela Superior de Física y Matemáticas del IPN como profesor de tiempo completo a través del programa de excelencia y tiene un puesto permanente como profesor desde el 2007. Es titular de la Academia Mexicana de Ciencias desde el 2012 y profesor visitante de la Universidad Estatal de Luisiana en 2013. El doctor Dong recibió un certificado de manos del presidente de Pakistán, Mamnoon Hussein, en el 49 Colegio Internacional de Verano. También recibirá el premio o la presidencia Lázaro Cárdenas, otorgado por el presidente de México, Enrique Peña Nieto, en el 17. El doctor Dong es investigador nivel 3, editor en jefe académico y miembro del consejo editorial de más de 10 revistas internacionales. Es autor y coautor de más de 320 artículos JCR, capítulos de libros, 7 libros editados, 9 libros publicados por Springfield, y cuenta con alrededor de más de 12,000 citas. Tiene un índice H de 69 según Google Scholar. Y podemos seguir diciendo más cosas. Sí. Es un gusto tenerte aquí de nuevo.
Sí, gracias.
Because you asked for the conference in English, Dr. Dong will take his conference in English.
Sí, puedo hablar español, pero...
Inglés. La gente quiere inglés.
Sí, hoy voy a presentar, ya salí aquí hace como 10 años. Me da mucho gusto venir aquí con ustedes.
¿Tienes aquí la Diana? No, sí, para que estemos
Entonces, muchas gracias a todos. También mi amigo, hoy tenía que conferir. Entonces, hoy, perdón. Nervioso, perdón. Hoy voy a. So the topic is quantum entropy in confined city. So, I think that you are here from here, but someone from the other group. So, with this topic, the first I work. The first part is the introduction, objective, and I will give the skill of the art, and then I will show the mathematical method, and also I will give the proposed model, and then I give the result, and finally I give the conclusion. So at this moment, the technology has been used in the construct the computer. For example, in 2012, the Nobel Prize in Physics is Haloch and David. They got the Nobel Prize in Physics because this work can be described as laying some of the foundational work, or represent the first step towards building a quantum computer, because in this work, the control is control how to control the particles or atom. Individual is elect the parity, use the parity control the particle or atom for this work. And then this year, sorry. This year, the Nobel Prize is this year is John, is 3 people, is John, teacher, and John, 3 people. With the power of the quantum mechanical theory, they will for the development of the qubit used in quantum computer today. Okay? So this year, so in 2012 and also this year, so 2 Nobel Prize about the cavity quantum, but all of the work are related with the quantum wave. So this is for example, this is Zhuzhang, the quantum computer is in China, 2020. This is and also 5 years ago is ABMQ, and this part is Google. This is 6 years ago. This is quantum computer. So this is at this moment the development of the quantum computer. So here is about the Entropy. For example, this Entropy is how to contrast. It's like the cavities. Entropy is in experimental. This Entropy is the laboratory Entropy, and this is Entropy. So, for example, here this is on the two wire. This is a double wire. This is the wire. This is another wire. It's a double wire. This is the particle. It's electron. For example, this one. This is the yellow part. Yellow part is this is a ground state. For example, this one ground state. This one is the yellow. It's the first excited state. So the particle from this part to here, and then this is the contract the two states. This is the ground state and the first excited state. This is the contract is a qubit. Understand? They connect the 0 and 1 superposition of the ground state and the first excited state. This state and this state. And two. So here I will give a brief view of the entropy. For example, here the many years ago, 1872, this thermodynamic entropy. This is a classic. And then static thermodynamic entropy in 1978 gives this. And then for example here, this 1988 is studies entropy. This and also is a classic. And this is von Neumann, 1932 the entropy. This density. This log density. This tree. Yeah. So here and also here is re entropy, 1961. But here today I will show this is the history, the development of the entropy. But here today I will give the two parts. One part is the sum entropy, the 1948. But here is a classic thing. Is a classic work for the by Sano, and here is 1925 is for the phase entropy. So this is today I will show you only this part and this part, phase and the Sano. Yeah. If you are interested, you can study this part and this part. So here, for example, here is the where. For example, this x1, x2 is like the two turning point. So here is this part is the where. This part is the where. the quantum wave. So I think that you are familiar with the process. It's the position, and also basically this is really finite range. Yeah. So today I will show you, for example, the Sano entropy is a quantum entropy. For example, this is the entropy in the position xa, but this part is the entropy in position. The sum of them is greater than this part. It's 1 plus log p. But here d is dimension. See? D is dimension. But this is the measure degree of the uncertainty in quantum thinking. This is greater than this part. This is the number 2.1414. This is the dimension. But here, I only study the one dimension. But and also you can study the 2 dimension and 3 dimension or high dimension. So 50 years ago, the scientists Becker and Pinowski and Piram and this is a professor from the Poland. So they proposed this uncertainty relation, but in quantum. So here I will give you the justification. So many types of the quantum systems are being explored, such as untrapped quantum dots, optical cavity, superconducting hoop, and asymmetric semiconductor wave to identify which one or work better for the quantum technology and the communication. So in this quantum system, entropy so as a key measure that have built the theoretical function and provide new insight into quantum system. Yeah? So this here, the quantum is we can explore. So the problem in quantum information theory, a key challenge is to describe quantum systems that can serve as the model for building components of the quantum future. These quantum systems are best suited for quantum computing and communication tasks. Maybe the quantum wave might be one candidate of them. So this is a general objective to study the entropy of the various confined multiple wave and hyperbolic wave to understand their property. So this is so in this talk I will give you two parts. One part is confined multi-wave and another part is hyperbolic wave. So this is for part is a specific objective. The first is to propose models for quantum wave that can be used in the construction of quantum device. And the second part is to study the entropy in the proposed quantum system. The third part is to analyze the result to obtain quantum entropy properties of the studied quantum system. So finally, to provide a theoretical basis for the design of the experimental in quantum computing and quantum computing. So this is for specific objective. Okay, so here I will show the speed of the art. So this is for example is 4 years ago the study of the entropy of this quantum wave, the qubit in a symmetric torsion potential. This is a semiconductor quantum wave qubit and associated Sano entropy 2 years ago. Yeah, this is 4 years ago. Selected some information. Entropy, some of the confined hydrogen atom and influence of the electron field. Yeah. This is 10 years ago studied with my student, the PhD student studied for through topic provide math Schrödinger equation. This is a projection method map. This is a Schrödinger equation. But this is a 7 years ago study that for the infinite sphere, the 3 dimension, and also the Fisher entropy. And also 6 years ago we studied the entanglement nature for the relativistic quantum information. But here, and also with the entropy, with Summer entropy. So this is for the W plus in initial state, but here is 6 years ago with my student and also with our student, yeah, the petrol part entanglement of the W plus in initial state is 6 years ago, and also all the top are in the relativistic quantum information. So I will show the mathematical measure here. This is the Schrödinger equation. This is the potential and the potential for given potential. We solve the Schrödinger equation, and then we can. So you know that we can get the wave function, and then from this wave function we can define the position interpretation. But here is the probability and the logarithm probability, and this on this position interpretation we can calculate the position entropy. So we can study the integral. And then, but here, if we use the Fourier transformation, use the wave function, get the wave function in the momentum, and then we can get the wave function in momentum, and then we can calculate the momentum introverticity. And this is the wave function in the momentum, and then we can also study the momentum entropy part. The problem is that here, sometimes we can get this part is easily, but sometimes it's not easy. But here, we have to use the numerical study this part. Okay. So here, we use the study the Schrödinger equation, use the Finite differential measure. But this is I think if you know this is the measure, Finite differential measure. With this one, we can get the this part right. The operator like is the diagonal the dimensional matrix, and then this is the BC, you can get the energy. Yeah. So here the tau 0 is like is content for this part. You can use this method with the numerical. You can get the wave function. Okay. If we get the wave function, and then we can get the wave function in the momentum use the Fourier transformation. Yeah? So here, in this talk, we give the what propose the model. But here we study 2 parts. One part is the arithmetic secret width. It means that here is a barrier, okay. But here the where the width of the where is different. But here is arithmetic secret width. For example, here the width is D, is a 2D, 3D, and 4D. For example, okay. And here is the width of the where is the same. This one same, but the barrier is different. For example, this is the one, the D, the 2D, 3D, 4D, 5D. For example. Here, another part is the simple hyperbolic where. This is the double hyperbolic where. This part. This is the simple where. This is the double where. So, how to write this potential in mathematically? So So here, for example, here, same match this part. For example, this is a barrier. This is where, this is where, this is where, this is where. Okay. But here, for example, here, we can define the potential in this way. Yeah. For example, for I 1, 3, 5, 7, for example, we can get this. Okay. This is the unit of the value. For example, this is a D to the 2D, or this is D, 2D, 3D, for example. But here, the value of the where is fixed. But here we take the 60 nanometers. The length of the where is the 60 nanometers. But here, this value, this where, the value. In quantum mechanics, we can, for example, we can use the Schrödinger equation, get this part. But here the two-way, okay, no problem. But the problem is 3 or 4, 5, 6, it's not easy. Yeah. So this is here, for example, is the where gives. This is the head of the where. Yeah. So this is the wave function. We found of the two-way for the ground state, the first excited, the second is excited. So you will find that the wave function basically is in the second part. This part is the first wave, this is the second wave. For them, the particle appears in this part. Okay? This is the wave function. This the blue is the ground state. Yeah, you will see that. So here, we can also plot the position and the momentum entropy density of the two waves for the ground, the first and second, and the third. For example, we can plot the density, the entropy density. Okay? This is the position. The this part is the momentum. But here, everything is we use the numerical. And also here, we will see that this is the position and the momentum entropy. This is here is we start the force 40 exact speed. Okay. The worst use is 20. The height of the wave is 20. This 200, 600 is 1000. Yeah. You will find that it's finally, if it's the height of the wave is the depth, the wave is very high, you will find that the particle is confined only the second part. It's the second wave. You see, this part no particle, but the particle is confined to the part. Yeah. Okay. But this is the first wave. This is the second wave. Yeah. Okay. So this wave. But here, when the depth of the wave is very high, so here the particle is confined to this part. But here, almost no particle, nothing here. So this is for the three waves. For three waves, so this is 1, 2, 3. Yeah? So this one. For example, this is 1000. The particle is moved here. This is the 4 waves. Here, and also we can start the 15 waves and the 22 waves. Okay, you can study, you can use the computer, you can study any wave, for example, because the length of the wave is fixed, is 60 nanometers, and also you can cut the wave, separate wave, so 15, 22 waves. Okay, so start the behavior of the particle from here. How to move? For example, here it's 1000. So we see that the particle moves this side. It's move to the right. Yeah. Okay. This is 15. This is 22. Yeah. Okay. Here we can study the sum of them, the position x and the momentum as p, you will find that the sum of the behavior, sum of the entropy. And also here is the sum of them, and also here. So here, another part is the barrier. Okay? For example, here, the width of the wave is same, is the same, but here the barrier is different. It's a D, the 2D or 3D, for example. The barrier, the width of the barrier is different. So here, it is a two-way, yeah? Two-way, three-way, and or four-way, yeah? Four-way. So if the length of the wave is same, 50 nanometers. But for example, here the number of the waves, 234, 15, 22, and the dupes we can take the 20. Sorry, we can take the 20 to 100, as in 100. Yeah? Okay. So in this case, you will find that here the bar is width of the body is here in this part is the first is very small. It's less than this one. This master. You will find that this body is very. It like the wall. It's very thick. Yeah. Okay. This part is thick. Okay. In this case, what happened for the we found the particle probability. For example, here, this is the two-way. The two-way for the ground speed, the fourth second, and the third precise speed. This is the blue. This is the ground speed. This is the red. The fourth. The third is the second and the third. Yeah? This is the waveform. This is a two-way. So this is the position instrument density. Okay? This is the position. This is yeah. But here is 20. This is 200. This is 600. Yeah? So you see that this is the way. This is the way. This is the first way. This is the second way. Yeah? Okay. You will see that the particle is very difficult from this way to this way because the body is very thick. Okay? The particle basically this part, the first way. Okay? This body is very thick. This is the barrier. The particle from this way to this way is not easy. Yeah? So here, for example, in the case of the four-way, yeah. One, two, three, four. Yeah, 1, 2, 3, 4, 4. But here, the value is different. This is the probability, this the position and the momentum entropy. For the four-way ground speed, first the second is okay. This is the position. This is the momentum. Yeah. So here, for example, in the case of the 15 wave and the 22 wave, so we can start the 15 and the 22. We will see the position and momentum entropy is different. Yeah. This is for the many waves, the 15 and the 22. But anyway, you can study different waves number. You can study 20 or 30. You only use the same program, but change the number. Yeah, this is the number of the wave. Okay. So you will see that for example, this is the depth of the wave is 20. This is 200. Yeah, with the increasing the depth of the wave, you will see the particle how to move. Yeah? But finally, with for example 1000, you will find that the particle is this size. this part is nothing. Okay? Only the first wave, this part. So this is some of the entropy in the position and the momentum. This is the position. The x, this part is momentum. This part is this part, the sum. You can see this part. Yeah. Okay. You will see that, for example, the number of the two, this is the number two-way. This is the three-way. Represent the two-way. But finally, with the inclusion of the number of the waves, you see that the sum of is no change more. For example, here. So now I will show you the hyperbolic wave, the simple. The hyperbolic wave, for example, here we study this part. But for this potential, I can tell you that we can get the solution exactly if the confluent hand function is very complete. But the problem is we use the confluent hand wave function. But the problem is we don't know the Fourier transformation, you understand? So it's difficult. So, but we know the solution exactly. But the problem is how to calculate the Fourier transformation analytically. At this moment we cannot do that. So we have to use the numeric to do part. So this is the wave function for the ground. First, second, excited the speed. This is the wave function. This is for the speed, the 6 exact speed, the 6 exact speed. This is the position and the momentum. This is momentum. This is the position. The entropy density. This is the U1, this is U2, this is U3, U1, U3, and for ground, 4th, 2nd, and 6th. Yeah, 6 exact. Okay. This is the single wave. It's a simple hyperbolic wave. So here, sorry. But here, for the 11 exact speed, the 11 exact speed. So, and also we studied the sum. Okay? The sum of the entropy. This is the position, the momentum entropy for the U1 to 3, okay? For the 11th exact speed. So you will calculate the how many exact speed? 11 exact speed here. Okay, this is for the high exact speed. Okay. So here, I will show the very interesting part is the fractional Schrödinger equation. Fractional Schrödinger equation. Before you know that the Schrödinger equation normally here is the 2, yeah? The 2, the delta is here, the number is 2. But here, if we don't take here is chi by 2 for the fractional, for example, k is fractional, so here is not the integral. So what happens? So how do we use the numerical study? It's not easy, but we can study the fraction for arbitrary. But here the k, comma k is between 0 and 2. The Schrödinger equation for double hyperbolic wave 1 and the second. So here, for example, here the comma equal 2, 1.5, 1.1, and 0.8. For example, here this 2. This is the Schrödinger equation for the chi bar 2 is a normal case, but here chi is very small, it's 1.5, 1 point, and also 1.1, and another part is 0.8. Okay? You will see that the wave function, but this part and here is very narrow. Yeah, this is very narrow. So here is the position, momentum, entropy density, or double wave for the ground, first, second, and the third. Yeah. For this position, this is the momentum. The momentum P. This is the PS. Here is for the case, special case 10 excessively. This is 10 excessively. And also, this is the position entropy density part. And here is the sum. Yes, this is the sum. The position and the momentum, the sum. Okay. But here, fx it means that is for the Fisher. So here we can study the Fisher entropy. This part is study the Fisher. But here, for example, here the chi bar 2 is 1.5, is 1.1, and 0.5, and 0, this is 1, this is 0.5. So this is for the Fisher entropy. So now I give you the conclusion. The fourth is the model and the framework for solve the potential in confined multiple point wave and the values with arithmetic frequency were diverged. The second part, the entropy, was used to describe this system, reinforcing its role as the perimeter in quantum modeling. The third part is the entropy of the single and the double hyperbolic wave were also analyzed using traditional Schrödinger equation and also fractional equation. Okay? But the traditional is chi bar 2, yeah? But here traditional, for example, chi bar 1.5, 1.1, and 0.8 for example. So this is the publication published in this part is from 10 years ago from here. So thanks for the invitation of the Daniel and also my previous student. Thank you.
Thank you.
Thank you so much, Professor, for the seminar. And I have a question. What is the role and is there a generalized uncertainty principle and functional Schrödinger equation? What is the role of this equation for solve the hyperbolic?
Oh, sorry. Fractional, yeah?
Sí.
This one? This one?
Yes.
But the k is between 0 and 2.
For example, what is the physical meaning of the...
Okay. For example, here, in if k is not equal to 2, so in physically, for example, in cloud, and also statistical physics, we use this part. If you are interested, I can show you some reference for k is not equal to 2. For example, a fraction is nonlinear and many reference. No problem. I can. If you are interested, I can show you the list of the reference.
Thank you.
You're welcome.
thanks for the seminar. I have a question. To which order can you take the arithmetic potentials? Can you take it like as high as you can in the order, in the spacing, or is there a limit in which?
Sorry?
In the arithmetic potentials, you have like 1, 2b, 3, and so on. Can you take it to any number you want? Like
basically, you can, for example, the length of the wire is fixed. For example, 16 nanometer. Yeah, it's like for example. But you can, in theory, you can cut. You can take any number. But the problem is, if cut is very slippery, you know, it's very thin. So in that case, I think the quantum theory is very, it's very clear. You understand? The part is very easy. For example, this one is very easy part. For example, its way is very small. You know, its number is small, 1, 2 way or 3 way. So it's like the ballet. It's not easy part. Yeah. So I think it's a quantum mechanics. I don't remember second character, and you should study how to solve the where, yeah, the finite. Yes. Yeah.
To determine how it can.
Yeah. But here you can choose arbitrarily any number.
Oh.
Yeah.
Okay. Thanks.
Hello. I have a question. Why do you propose to use or still in multiple the hyperbolic welds? Or is there something special with the hyperbolic welds for a student, or you can use another kind of potentials like Yukawa or something else?
I think you can use any potential.
So there is no something special with the hyperbolic?
For example, here we are studying this part because 2 years ago we gave the exact solution for this part, for this potential. The solution is confluent hand. See? Right here? This one?
Did you use another color? It's better than the white. Because it's not.
Okay, confluent. So, the problem is this equation is very complete. Okay? For example, we studied the Ernst, retard, and you know that, see, Young, see, and also Laguerre, for example. But this function is included them, specifically, for example. So the problem is for this part is alpha beta or gamma, for example, is variable r, for example. The problem is this is wave function, for example. The problem is energy include one here, maybe here, maybe here, maybe here. Understand?
Okay.
Inside, involved. So I call this solution is semi-exact solution. See?
Okay. Thanks.
The problem is energy we cannot get exactly. So the problem is here. This will function. No, we cannot get the wave function. Use the Fourier transformation. We don't know how to do this. Hold on. See? This one and the transformation is difficult for this one. So this is reason we have to use the numeric. Here, confluent, and also there are 3 different functions. There is a libel book You can check, no problem.
Hello, Doctor. Thank you for the nice talk. I have a question. What happens during a quantum measurement in confined systems? How does it affect a system of entropy?
Sorry, could you?
What happens during a quantum measurement in confined system?
Okay. Confined system, for example, confined system is the wave function must be zero. For example, is a limit, yes, is in fixed grid. This, for example, here. For example, here, this is a salon. This is a ballet, yeah. This is from, for example, this is a 0x, for example. This is infinity. The particle cannot pass this part, particle cannot. This it means that it's confined. So, for example, here to where with the depth of the wave, so particles for the is very deep, so deep. So the particle is very far down here. It's like a gas area, then it cannot go out. And I like, for example, this one, no, this one. For example, harmonic oscillator. For this one, the X is the whole state, you understand? So, for example, here, the potential is the infinite, no, minus infinite, this is infinite. The whole state, this is the, we cannot say is the confined, because it's the whole state. But confined, it means that this one, for example, the integral A and B, the wave function, you understand? So, this part is the field. This must be equal 1, for example. Okay?
Thank you, Professor, for the nice talk. My question is that, is there any way to apply this quantum entropy to the quantum chaos or the many body systems?
Here is only the field body. Field body. No.
There is no way to apply quantum entropy to the method of quantum chaos and the many body system.
I think you can study main body, two particle, three particle. I think you can use the simulation, but I don't know. But
how we can apply this quantum entropy to multi-particle entanglement?
Okay, you can do that. You can
how
do
we
that.
can relate the multi-particle entanglement to the quantum entropy?
I don't understand your question. What?
My basic question is how we can apply quantum entropy to the quantum chaos or many body systems. But okay, I can study. This is not my topic. And another question is that how we can apply this quantum entropy to the multi-particle entanglement system.
Entanglement.
Yes.
Okay. But here, look, how to entanglement is, for example, it's a particle, the wave function. The wave function we cannot simply understand. It's like the hydrogen atom, understand? We've shown, no. With the wave function, but here is only one particle. One particle is how to is the problem is here. For example, no, sorry. This is a ground state, yeah. This is the first excite state, for example. So here, this is 0, this is 1. If we use the superposition from here, from ground state to the excite state, the superposition, for example, with functions. In this case, we can use with contrast the entanglement state. You understand? You see one? For example, here, from here to here, if we give the absorb the energy from here, emits the electron or photon, this state is the ground state 0. This is the first excited, for example, 1. So between them, maybe contract a superposition, you understand? 0 or 1, we can contract the entanglement between them. Okay? It's like this one, for example, here. This one, for example, here. This is the ground state, and this is the one. The first excited. So, and then between them, so here we can realize the entanglement. See?
Good afternoon. My question is about, for the second proposed model, in some part you use 15 and 22 barriers. Is there a particular reason for these numbers? Or
15, yeah?
15
15
and
where?
22 barriers, yeah.
Okay.
For the second proposed model.
50 for
The second one.
hypothetical? No,
The second model.
second one. Sorry. Barrier, yeah? This one, yeah?
Yes.
Okay. So the 15 is, but here I don't show because we can use the computer, the Raimondo, design the program, and then use this one. Okay? For example, we take I number, for example, 1, 3, 5, 7, but here 2, 4, understand? In case of the 1, 3, 5, 7, we can use this one. Then with the number. For example, this is 1, 2, 2A. This is 1, 2, 3, 1, 2, 3, 4, and 5, 6, 7, 15.
Okay.
And then but the length of the where is fixed 60. This one, 60 nanometer. But we can separate like this one. Understand? Here 1, 2, 3, 4, 5. 1, 2, 3, 4, and then 15.
Thank you. I didn't get that part.
Yeah. But here you can hear, yeah. But the length is very fixed, is 60.
Thank you.
You're welcome.
Thank you. My question is about the simulation and graphics. In what programming language were they done?
Sorry?
About the simulation, in what programming language were they done?
Okay. Use my student Dr. Raimundo used MATLAB. I think they use another student used Python. I don't know because
Okay, thank you.
see?
Hi, thank you for the lecture. When you were introducing the different types of entropy, I remember that I heard about the von Neumann entropy related to entanglement and quantum technologies, and the Shannon entropy for information theory.
Yeah.
So my question is, why do you have different entropy models? Like, are they measuring the same thing, or like the degree of this uncertainty, or why do we have different kind of things?
Okay, thank you. The entropy is different. For example, here is Sano. Sano entropy is normally studies localization. Yes, localization behavior. For example, it's 16. For example, it's the particle is stable or not stable. And the feature is like is a global. This is a local. Okay. This is a sun, for example. This is a global. By the 1948, this is a classic. Classic, but there is a sun. It is related with the probability. But in 1975, three professors, Bologna, and so the sun change the integer. It's because the variable is x continuum. So this is a different. This is a localization. It's stable. The thinking. Yeah. Okay.
Thank you very much.
Hi, thank you for the conference. I have a question. We know that in classic thermodynamics we can have the process with zero change of entropy doesn't exist in reality, but we know the concept that if we have a zero change of entropy, that means that the system is getting through an infinite states of equilibrium in an infinite time, all the time of the universe and more. So my question is if with this definition of entropy that you mentioned, is possible to have a zero change of entropy process, and what would that mean?
Division?
Hmm?
The division?
That we use the definition that you use in the definition of entropy that you use in the definition
The actual of puedes hablar
Sí. La definición de entropía que utilizó desde el inicio, la que le acaba de explicar así. Sí.
Shannon.
Sí.
But you can puedes estudiar otro tipo de entropía, pero nosotros no estudiamos porque te digo la verdad que mi alumno no como ustedes de la gente aquí, porque ustedes son ¿cómo se llama? Críticos, ¿sí? Que mi estudiante de la mayoría, algunos sí vienen de física, pero la mayoría vienen de computación, ¿sí? Porque yo trabajaba aquí, entonces yo sé, ustedes saben muy bien de física, matemáticas, ¿sí? Pero el mundo no sabe mucho de conceptos, por ejemplo, entonces otra tipo de entropía, perdón, no trabajamos. Entonces él nada más trabaja este tipo de Sano. Fisher también, porque allá también usa la probabilidad. Entonces, otro tipo, conocemos muy bien, hace como 10 años, 15 años, trabajamos mucho de Sano. ¿Sí? Pero Sano sin relación con localizar, behavior, local behavior. But Fisher entropy is global. Global. But I don't understand your question is what definition of what? But here we study.
Sí, quería saber si, ¿qué significaría un cambio cero de entropía?
Zero.
Ah,
Zero it means that the probabilidad is fijo. Ya sabes, por ejemplo, ya tiene lluvia, seguro. Ya está lloviendo, por ejemplo. La probabilidad ya cero, logaritmo 1 igual 0, por ejemplo. Tiene más posibilidad, ¿cómo se llama? Menos posibilidad, entonces entropía, pero si la cosa es muy ya fija, ya hecho, ¿se me entiende? Si probabilidad igual 1, por ejemplo, entonces, perdón. Pero, si probabilidad igual 1, por ejemplo, tú, aquí, ya, así tengo como. ¿Cómo se llama? Por ejemplo, un carro, ¿sí? De Schindler Car, ¿sí? ¿Sabes? ¿Eso? ¿Sí sabes? Carro de Schindler. Antes de entrar, por ejemplo, si abre la caja, ¿sí? Antes de abrir, tú no sabes abrir o vivo, ¿sí? La mirada, por mirar. Pero cuando abre la rueda a la caja, entonces sabes, seguro, murió o vivo. Entonces, en este caso, la probabilidad es cero. Ya porque ya no tiene probabilidad. Si por ejemplo así, la mirada, sí, grande. Cuando ya abrió, entonces ya sabes, seguro, ya murió o vivo. Entonces aquí, igual, cuando sano igual, X igual 0.
bueno.
Ya no tiene cambio nada. Estable, porque ya el punto es 0.
Sí, ya tiene probabilidad constante. Probabilidad, sí. Bueno,
Brian.
Hi. 谢谢。
Brian.
How many physical qubits do you need in a base in an ion trap to make one logical qubit?
Well,
How many qubits do you need? I don't know, how many physical qubits do you need in an ion trap quantum system to generate a logical qubit?
So you mean that for the computer, construct the computer or what?
I mean, when you,
For example, is now all students study the 27 qubit, for example. See?
I mean, you want to scale all this approach and the system. How is behaving the system or the error? I mean, okay, in the quantum systems, there is a measure that if you decide in which kind of phenomenon, system, or I don't know, approach.
But here, no, here, study here, no relation with the qubit, no. But here, this system,
Okay, with that you cannot
no
manage the
qubit,
qubit.
no, nothing. But another student, I think maybe from Pakistan, I don't know from where, from
Okay.
India. So
In which
we
case,
can contrast, because for example here, the superposition 0 or 1, okay, with the entanglement. But here we know, here only study the
zero entropy,
Okay.
nanoqubits.
But here, but there I mentioned the qubit is mean that the point where here you can release the pooling. But this one releases the quantum computer, understand? Physically. But here we study the input sound. It's a way release the pooling. For that, for this part, it's a get the number is one, yeah? It's to sort out the term and this year. So this one is release the quantum computer.
Okay, when you stabilize
But here
the
no, here nothing.
entropy well, you will have the
Maybe
change.
in the future we can how to contract it is the how to contract the 0 or 1, for example, is contract the big part. Yeah, the superposition. Is there.
I understand. Thanks.
No, no.